Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by one of my colleagues from Janssen, Dr. Christopher Kelly. Chris got his bachelor's in biochemistry from Stonehill College before coming to the University of Connecticut for his PhD in the group of Professor Nicholas Leadbeater. He subsequently did a postdoc at the University of Pennsylvania under the supervision of Professor Gary Molander, where he became an NIH NRSA postdoctoral fellow. He then became an assistant professor at Virginia Commonwealth University, as well as a lecturer at University of Pennsylvania, before joining Janssen in 2019 as a scientist in the Discovery Process Research Group in Springhouse, Pennsylvania. And with that, I'll hand it over to you, Chris. Thanks a lot for coming on today to share your chemistry with us.
Thank you, Matt, for that kind introduction and for the invitation to present some of my work prior to joining Janssen on Synthesis Workshop today. As your audience can see, the title of my talk is Radical Polar Annulation Reactions, which myself and my co-authors have affectionately dubbed RPARs, referencing a common NMR command. In fact, RPAR processes are remarkable workhorses for ring construction, which I hope I will be able to demonstrate to your audience today. To set the stage for our discussion, I would like you, the viewer, to consider what words come to mind when you think of radical chemistry. Perhaps you think of uncontrolled single-electron species that are highly reactive. Perhaps you think of chain processes in those canonical three steps, initiation, propagation, termination, you learned as an undergraduate in organic chemistry. Or you may think of some common radical reactions, like radical bromination, or that weird outcome that happens when you add HPR with peroxides and an alkene. In fact, radical reactions are becoming critical for synthesis, even if it's taken the organic chemistry community a while to get here. Recent developments have taken what was initially stoichiometric radical processes and moved them into catalytic manifolds, leading to dramatic discoveries that have really pushed the boundary of organic synthesis. Indeed, radical reactivity enabled by a dash of a photocatalyst and some good old visible light can allow previously unimaginable transformations to be accomplished with ease, and these range from cross-coupling to heteroatom bond-forming reactions. In order to properly have a discussion on radical chemistry, we must first discuss how we have become so proficient in the generation, and that comes from photocatalysis. Visible light has a lot more energy than we traditionally provide to our reactions, which in our reactions we traditionally provide infrared radiation. We can see that the energy density of visible light is more than double that of IR per unit of energy, meaning that we can deliver more energy per unit time to our reactions, with the added benefit of being able to stop the reaction at any point with the flick of a switch. UV irradiation does provide more energy than visible light and does have the benefit of being absorbed by organic molecules, but this often leads to molecules getting what I'd like to call sunburn and leading to a lot of untargeted, undesired radical reactivity. The problem with visible light is that it's hard to tap into its energy. We, as chemists, have come up with a solution that nature has known for a very long time, which is to use a visible light antenna to capture that energy from light and turn it into chemical energy. Whereas nature uses chlorophyll, we use photocatalysts. Beyond simply looking cool, blue LEDs can photoexcite a variety of photocatalysts to singlet excited states, which can then engage in intersystem crossing to generate a triplet excited state. Quenching of this triplet excited state can be accomplished by either reductive or oxidative quenching, meaning that you can reduce or oxidize a substrate. From there, the reduced or oxidized state of the photocatalyst can reduce or oxidize an additional substrate, respectively. I like to think of a photocatalyst as a wire in an electrochemical cell that is facilitating the transfer of electrons between different substrates. Since these processes are governed by single electron transfer reactions, electrochemical principles become very important, and we can establish redox windows in which photocatalysts can operate. These windows are key for predicting what may be the most appropriate photocatalyst or may not be the most appropriate photocatalyst for a particular transformation. It can also be useful to predict whether there's going to be any undesired oxidation or reduction of components of that reaction. So as I just mentioned, we can use redox potentials to select a photocatalyst, but we can also use it to predict reaction success. We can hypothetically imagine a radical-radical coupling reaction of a persistent radical and a transient radical to make a CsP2-CsP3 bond as shown on the screen. So prior to even starting this experiment, we can predict whether this reaction will be successful on redox potentials alone. I've provided the redox potentials for the two components of this hypothetical reaction. What we are trying to do is marry these two single electron transfer processes for productive reactivity, and to do that, we need a photocatalyst. If we do a little math, we can see that the oxidative quench of this photocatalyst excited state and the oxidation using the oxidized photocatalyst ground state yield positive cell potentials. And as we know from undergraduate organic chemistry and undergraduate general chemistry, this leads to a negative delta G of reaction and is thus favorable. To put it all together mechanistically, we first photoexcite our photocatalyst to an excited state, engage in oxidative quenching to produce a long-lived radical anion of the dicyano component, then oxidize the carboxylate to generate a transient alpha nitrogen radical. The two then pair up to give what resembles a Meisenheimer complex, which will then aromatize to give the desired product. This is, in fact, a real reaction reported in the early days of the modern radical renaissance by the MacMillan group. So, where does radical polar crossover fit into all this? Radical polar crossover effectively marries radical and polar reactivity by proceeding through radical and charged intermediates. Two modes exist either through anionic mode, or which I dubbed mode 1, or cationic mode, which I've dubbed mode 2. Although not limited to photocatalysis, the focus of our discussion today will be on photocatalyst-driven radical polar crossover processes. An example of a mode 2 type process is given below, reported by Liu and coworkers in 2014, and is an example of an RPAR type process, in that it makes a ring through a radical polar crossover process. As you can see, there are two key steps, the so-called Giza addition of an aeroradical to an alkene, mimicking Michael-type reactivity, and the intramolecular attack of a radical by the carboxylate in what constitutes a polar step. Now, before we get into RPAR, which is going to be the focus of our discussion, and is a mode 1 type process, we need to introduce the viewers to common radical precursors. So on the top of the screen, you see 4 different radical precursors, carboxylates, silicates, organotrifluoroborates, and dihydropyridines, that were around at the time this work was being done. There are newer radical precursors, and these include anything from siloamines to primary alcohols to even just activated CH bonds to amines. But at the time, there was a limited suite of radical precursors that were available, and the focus of today's talk is going to be on these hypervalent silicate species. So how do you access these hypervalent silicon species? Well, it's in fact quite easy, and actually I have a organic syntheses paper published with an undergraduate who made a vast majority of these silicates. And it's a very easy reaction to conduct. You simply mix a trimethoxysilane, catechol, and an amine, and you can get reliably good yields of these nice white powders that represent these hypervalent silicon species. And you can see that there's a great deal of structural diversity that comes with these radical precursors. The only thing that's better than their structural variability is the number of transformations that you can do with these hypervalent silicon species. You can do anything from thioesterification to CsP2, CsP3 coupling to vinylation reactions to imine alkylations. But the focus today is going to be on this cyclopropanation reaction. Now, cyclopropanes, if for anyone that knows me, are definitely a passion of mine, and for good reason. They're very structurally interesting. They're very strained molecules, but also because they are commonly featured in a variety of medicinally active compounds. Cyclopropanes sort of mimic the geometry of an alkene, but sort of have increased solubility because they're actually CsP3 hybridized. One particular submotif that I am always interested in are trifluoromethyl substituted cyclopropanes, harkening back to some work I did as an undergraduate. Trifluoromethyl cyclopropanes are actually viable isosteric replacements for alkyl groups, specifically terp-butyl groups, that lead to longer lifetimes in biological systems and lower clearance times. And we can see that this particular motif is gaining traction in the medicinal chemistry community as it's starting to appear in clinical candidates or as a way to improve metabolic stability on existing scaffolds. So, how do we deconstruct a trifluoromethyl substituted cyclopropane? Well, one way you could consider doing this is by installation of the trifluoromethyl group itself onto a cyclopropyl scaffold, or maybe perhaps bring the CF3 group in while you're making the cyclopropane. The other way is to take an existing trifluoromethyl substituted cyclopropane with some sort of nucleophilic or electrophilic handle and install it onto the desired target. Or you can in fact build the ring around the trifluoromethyl group, to which I've actually had some success in my past life as a graduate student, by either cationic or anionic ring closure. And I want to draw your attention to the anionic ring closure type processes, these addition cyclization or Corey type processes, where we take a nucleophilic carbon source, add it into an electron deficient alkene, and promote some sort of cyclization event. Now I want to take a closer look at these two anionic type cyclizations. In both cases, the key step is an intramolecular nucleophilic displacement reaction in what constitutes a 3-exotet type cyclization. What distinguishes these two processes is whether the leaving group is brought in with the nucleophile or was part of the olefin initially, a theme that will crop up later in my talk. Regardless, both rely on carbon nucleophiles and electron-poor CF3 alkenes, which preclude certain CF3 cyclopropanes from being prepared in this fashion. As a solution to this, I considered what would happen if I used a radical polar crossover process to facilitate annulation. In the first step of the envisioned process, you would engage a CF3 alkene with a radical bearing a leaving group at the alpha carbon. This would constitute a Giza addition to the alkene and would generate an unstable CF3 radical. This unstable CF3 radical will then be reduced by a photocatalyst or some other source to generate an anion which would engage in 3-exotet type cyclization as seen in the previous examples. Now, this idea of making cyclopropanes by radical annulation was not new. It was actually inspired by some work by Xuan and co-workers who used diiodomethane to generate similar intermediates, which under his conditions cyclized by way of a radical ring closing event. With this paradigm in mind, we needed to design a reagent to accomplish this task, and the reagent that we sort of settled on were these halomethyl silicate reagents. Now, chloromethyl trimethoxysilane was available at the time, and we were able to use it to prepare the corresponding silicate. We then took this silicate and subjected it to standard photoredox conditions in the presence of a CF3 alkene, with the anticipation that perhaps we would see cyclopropanation, and indeed we did. What we saw was a 93:7 ratio of defluorinative alkylation to cyclopropanation, and the defluorinative alkylation was not really surprising to us at the time because we had previously reported a process in which we were doing this selectively to make gem difluoroalkenes, and the mechanism is shown below there. Now, thinking to undergraduate organic chemistry, if I want to increase the rate of a substitution process, I use a better leaving group, and indeed that was the solution that we came to here. We were able to prepare, with some little bit of extra effort, iodomethyl silicate from iodomethyl trimethoxysilane. Now, we had to modify our conditions and shorten the reaction time because this reagent in solution is quite unstable to thermal conditions. But will precipitate out during the reaction process in neat triethylamine, and you can get this nice off-white powder. Using this reagent, we were able to show that indeed there is a dramatic change in the reaction outcome in that cyclopropanation became the exclusive product. We can even see the transition between cyclopropanation and defluorinative alkylation as we change from chloro to bromo to iodo. With this success in hand, we wanted to see if we could optimize the condition to maximize yield, and indeed we pursued a variety of different optimization efforts looking at solvent and photocatalyst structure. We wanted to transition away from organometallic photocatalysts to more organic, more sustainable photosensitizers, eventually selecting this 4-CZ-IPN, which our lab has affectionately dubbed ZippinCat, as a way of facilitating this transformation. And indeed, this was the optimal catalyst for this process, allowing cyclopropanation on this model system to be effected in only 3 hours in quite good yield. Using these optimized conditions, we wanted to probe how diverse a subset of CF3 cyclopropanes could be generated using these photocatalytic conditions. And the answer to that question was that it could produce a wide variety of CF3 cyclopropanes, including those that were generated from free ammonium salts, to free carboxylic acids, to those containing other alkenes, to a variety of different heterocycles. So we're very pleased with the type of diversity that we could generate using this reaction. So in addition to being a very diverse transformation, this reaction was extraordinarily easy to set up. You would simply take your components of your reaction, put them in a vial, remove the atmosphere and replace it with argon or nitrogen, and add your solvent. You would get a nice yellow solution, which you would then irradiate with blue light irradiation, and after 3 or 4 hours you would get this nice white precipitaty or yellow precipitaty solution, which would indicate the reaction had reached completion. Now the cool part is you didn't necessarily need to use blue LEDs. If you were willing to wait a little bit longer, you could simply just use 20 to 21 watt CFL lights, which would do the same task. When developing a new transformation, one of the most important things to me is understanding the mechanism, and this reaction was no exception. Considering how this mechanism was occurring, there were 2 mechanistic proposals that myself and my coworkers had discussed as potentially leading to the cyclopropane product. One was an SH2 or radical type ring cyclization as proposed by Xuan, and the other was more SN2 type or 3-exotet type anionic cyclization. And of course I wanted, the RPAR one to be right, but at the time I really was convinced that we were going through an SH2 type cyclization. And this was actually supported by the fact that the ratios of fluoride elimination to cyclization didn't change with ring electronics and were really insensitive to the presence of acid. In fact, if you look at the counterion for the silicate, it is an acid itself, so this lends support to a radical type process. Although this data supported the SH2 type cyclization, we weren't convinced, and as such we turned to computations as a solution to this conundrum. We partnered up with Osvaldo Gutierrez and his group at the University of Maryland, now at Texas A&M, to evaluate the both radical and anionic pathways. Oswaldo and his group were able to generate the data that you now see on your screen for the radical 3-exotet type cyclization. And what you see is that the trends in reactivity do align with experiment. However, the barriers for cyclization from iodomethylsilicate are the only ones that are feasible under our reaction conditions. Both bromo and chloro are too high to have occurred at the near room temperature, 25 to 35 degrees Celsius, reaction temperatures that we run these reactions at. Further, the fluoride elimination pathway was way above 60 kcals per mole and is certainly not radical in nature. As such, we turn then to the data that was generated by Oswaldo and his team reflecting the anionic ring closing pathway. And here's where everything started to make sense. We can see on the right-hand side that the barrier for fluoride elimination is independent of the halomethyl radical that was added into the CF3 alkene, meaning that it's constant across the different halogens. However, on the left-hand side, you can see that the anionic 3-exotet cyclization is dramatically impacted in terms of its activation barrier by the nature of the halogen, which is to be expected. As you would expect in undergraduate organic chemistry, the better the leaving group, the faster the rate of the reaction. What we can see is that the barrier for cyclization from iodomethyl radical addition, followed by reduction in anionic ring closure, is much lower than that of the fluoride elimination pathway, meaning that that should be the preferred, if not exclusive product, which is what we observe in experiment. Likewise, as what we observe in experiment, the barrier for chloride elimination is much higher than that of fluoride elimination, meaning that we should get selectivity for fluoride elimination over chloride elimination, and that is indeed what we do see. Thankfully, it wasn't high enough to be exclusive, otherwise we may not have discovered this exact reaction. So the trends that are observed here exactly reflect that in experiment. However, we took the calculations one step further. Oswaldo and his team calculated what would happen if we added not into a CF3 alkene, but into a diphenyl alkene. And he compared the radical cyclization to the anionic cyclization. And what we found was that the mechanism is for sure universally anionic, in that the blower barrier pathway for cyclization will surely be by way of anionic ring closure. And what that means is that we should be able to use other alkenes so long as we can get radical addition, and perhaps even use the iodomethyl or chloromethylsilicate to facilitate annulation. So that's exactly what we did. So what you can see here in this slide is that we can get similar yields, at least when permissible, of radical addition to the iodomethylsilicate as in chloromethylsilicate with a variety of different alkenes. Now, this is not universally true because the radical felicity of chloromethyl radical versus iodomethyl radical are vastly different, but in situations where they're comparable, we can see that we can get cyclization with both iodomethyl and chloromethyl radicals. Now, this is where the story for at least RPAR Part 1 ends, but there's always a way to expand on your paradigm if it's good. And indeed, what we were able to do here is draw back to that addition cyclization mechanism that I told you about earlier, wherein rather than bringing in our leaving group with our radical, we were going to have our leaving group already installed on our fragment that we'd be adding a radical in. And this was exactly reflective of that first addition cyclization type manifold that I discussed. So why would you want to do this? Well, the original report that we had for RPAR was not very modular. It really could only add a CH2 group, and really we were limited to silicates as our radical precursor. We couldn't use BF3Ks or dihydropyridines at the time. So what we thought of was perhaps if we put the leaving group on our alkene fragment, we could trigger the same type of 3-exotet type cyclization. Now, what would be great about this is it would expand our repertoire of cyclopropanes that we could make to a very high degree. So what you can see here is that we have our radical adding in a Giza-type fashion to generate a alpha radical, which will then get reduced to generate an anion and result in anionic ring closure. Now, this opens up a suite of different radical precursors, so virtually we thought we could make any type of 1,1 disubstituted cyclopropane imaginable using this model, but we had to test it first. And so using very similar conditions to those derived for the CF3 cyclopropane synthesis, using for ZIP and CAT, DMSO or DMA, and a variety of different radical precursors, we were indeed able to expand on the RPAR paradigm to what I will call RPAR Part 2, wherein we were basically able to add radicals to alkenes that had a pendant leaving group, in this case a tosylate. We can see from the nature of the cyclopropanes that we were able to generate in this report that it very much mimics the types of transformations that we could do with the CF3 cyclopropanation reaction. We're able to tolerate structural complexity and heterocycles. Further, we're able to generate a wider variety of cyclopropanes because we can pull from 3 different radical precursors. We can pull from silicates, trifluoroborates, as well as dihydropyridines, and we can install secondary, tertiary, or even primary radicals into the alkene and trigger the 3-exotype type cyclization. Perhaps the most phenomenal thing about this reaction, and speaks to the strength of our understanding of the mechanism of this process, is the fact that the origin of the radical doesn't matter when it comes to the success of this reaction. Sure, the conditions may change because that involves how the radical is generated, but the actual origin of the radical doesn't matter so long as you get to that same radical. So what we did is we set up 3 tandem experiments wherein we would generate the same product and generate the radical by 3 different ways. The first, we used the trifluoroborates that I mentioned before as the radical precursor using our standard conditions. We then modified our standard conditions to adopt protocols that would generate radicals from carboxylic acids as well as activated CH bonds. In all cases, we were able to obtain pretty good yield. The fact that we use a tosylate in this reaction also rules out the SH2 process that I mentioned before. So the mechanism that I talked about with the trifluoromethylcyclopropane reaction carries through here into this, what I would call RPAR Part 2 reaction. Believing RPAR to be a paradigm for annulation that was simply untapped, my team at VCU, in collaboration with the Molander group, pursued the synthesis of bicyclic systems by way of the RPAR paradigm. We prepared vinyl tosylates from simple tetralones and indenones and then subjected them to the photocatalytic conditions. We were able to show that both trifluoroborates and silicates were competent in generating these bicyclic systems. Another very interesting report was done during my time at Penn that is an RPAR reaction but doesn't involve cyclopropanes, and this was a pretty cool report. What we did instead in here is we took imines as radical acceptors and varying chain length haloalkyl silicates, and were able to subject them to RPAR type conditions. And in this process, what we were able to see is that we got radical addition to the imine, generated a nitrogen anion which would engage in a cyclization event. And we were able to generate both piperidines and pyrrolidines using this type of chemistry, and also bicyclic systems as well. And so what this does is it really demonstrates the strength of the RPAR paradigm. And so sort of in closing here, I want to leave you with this idea that RPAR is a way to allow us to construct very complex systems, be they cyclopropanes, be they bicyclic systems, or be they saturated heterocyclic systems, all using a very simple catalyst, this 4-CZ-IPN catalyst, or other related photocatalysts under innocuous conditions. As a rule, I personally believe that the best science is done in collaborative environments. None of the work that was presented in this week's Synthesis Workshop episode would have been possible if it were not for the strong collaborative bonds that I had forged within and outside of the Molander group and within my own group at Virginia Commonwealth University. I want to recognize a few individuals that were instrumental in bringing the RPAR vision to life. In particular, I want to recognize Dr. Simon Lang and Dr. Rebecca Wiles for their work with me on the defluorinative alkylation process. This reaction really set the stage for RPAR's later discovery. I want to thank now Professor John Milligan, Dr. James Phelan, Dr. Victor Polides, and once again Dr. Lang, as well as the Gutierrez group for the tour de force efforts on the back-to-back reports on RPAR. I would also like to acknowledge my awesome team at Virginia Commonwealth University. They were a hard-working bunch and all were able to publish during my tenure in Richmond. Finally, I would like to acknowledge Dr. Loic Pantine, Dr. Jennifer Matsui, and once again Professor Milligan for their efforts on the heterocycle synthesis using RPAR. And of course, I would like to thank Professor Gary Molander for all his support and guidance over the years. If you have any questions about the work presented today, feel free to reach out to me.
Thank you for joining us for this Research Spotlight episode, and thank you very much to Chris for sharing your work with us. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.